Hello, good afternoon. So my goal today is to tell you about how to create artificial intelligence. And by that, I don't mean artificial intelligence that you have in your telephones right now. I mean the artificial intelligence that we would really like to have, the one you see in movies, for example, a robot that you would have at home, and you could send to make up your room, or to prepare your meal, or to help you with the homework, but not do the homework for you, just help you with the homework. And to do that, I will have basically several parts. I will tell you about a new brain-mind theory that has been recently developed. I will tell you how does this theory apply to artificial intelligence, or AI. I will tell you why we need something like a kindergarten in which we will play with the robots in order to develop such intelligence. And then I tell you something about the safety. It's very important that AI is safe, that it doesn't, once it becomes intelligent, that it doesn't start ruling the world. We want still us to be the ones who rule the world. Right? So to begin understanding about what intelligence is about, we have to think in terms of agents that interact with the world. So the goal is basically to have an agent, which is in here, this gray box, that has a knowledge what to do when. There is interaction with the external world, there's some sensor inputs, and then the agent has to know what to do. If it knows what to do, it's intelligent. The more it knows, the more intelligent it is. That is the basic idea. Now, the main question is how to get that knowledge. Where is this knowledge going to come from? And what we have so far today is a solution of this form. You have another mechanism, another system that actually also interacts with the environment, gets an input from the environment, and then makes changes within the agent and basically teaches this level of agent on what to do. Normally in neuroscience, we call this neural plasticity, whereas this part would be the neural network that interacts. In artificial intelligence, you would call this part a policy, whereas the lower part would be called something like learning mechanism, right? Now, this one we can describe as T1. It has only one level of interaction with the environment. The other one we can describe as T2. It has two levels of interaction with the environment. Here's an example of an artificial neural network. The dark part is the top level that interacts with the environment, has knowledge on what to do, hopefully. And this orange part, red-orange part, is the part that learns, that teaches the network what to do. It makes a comparison between what has been done and what needs to be done, makes changes to these synaptic weights, and then teaches it. This T2 structure is how we think today about the brain, and it's also how we think today about artificial intelligence. We think in terms of one level that performs the behavior and another level that trains the system to perform the behavior. However, what the new theory tells us that we actually have to have three levels. We have to have a T3 system. And let me walk you through the idea how it works in our own minds, how our own minds work with three levels. At the lowest level, we have genes. Genes are our basically learning mechanism, our plasticity mechanisms. These genes create our long-term memory. This big blob that you see are our long-term memory. However, the theory tells us this is not yet finished product of an agent that can interact with the environment. We use this long-term memory only to adapt once again at one new level. So the long-term memory is not the knowledge on what to do when, but it's the knowledge on how to adapt, how to learn. And then we learn quickly with very fast process, and we create something really higher up, which is called working knowledge. And that's a knowledge that momentarily is used for this particular situation. And only then can be produced a behavior. So for example, if an agent has to, or if a human has to interact with a chair, it has to recognize a chair. The traditional theory would tell you there's a system that takes inputs and then raises something like, oh, here's a chair. What this theory tells you, what we do when we see a chair, we actually reprogram the entire neural network of the brain such as to prepare it to interact with that particular chair, not with any chair, with that particular chair that we see right now, the sensory input that is coming. And this requires these 3 levels of organization. And they work with different speeds. The highest one works the fastest. This is the sensory motor loops. The lowest one is the slower one, that's the learning. And the medium one is this new one. That is fairly fast, but still it's slower. It's medium fast, right? And then whenever it goes red, this medium one, this is the moment where a new thought comes about or new reconstruction of the system comes about. With that, we can build a whole theory of a mind, explanation. It's called the 3 traversal theory of the mind. At the bottom, we have learning rules, psychological drives, our instincts. Then comes a learning process, which creates long-term memories. But these long-term memories, as I said, this is not a ready network. You still have to apply those in order to create a ready network to interact. And this process of application of those are our decisions that we make, are the process of recognizing object, paying attention, and so on. Then we create the contents of working memory, attentional selection, expectancies, and such things, and only then can we interact with the environment. Now, this has implications. What does it mean? What is the thought? What does it mean to think? Traditional theory of what does it mean to think basically makes thinking equivalent to mathematical mapping functions. So you have some set A, set B, and a mapping between A and B, from sensors to muscles. That would be the traditional way where you have just T1 process of thinking. But if you have 2 levels of organization which we think, then a thought is something else. Then a thought becomes a change in the computational properties of neurons. It's not anymore just a computation. It's a change in properties that occurs through the interaction with the environment. So in other words, a thought is an adaptation. So much like you can think in theory of evolution, species adapt, change their properties. So thought is pretty much conceptually the same process, just occurs much faster. That's one difference, much, much faster, of course. And the other difference is that it is much more informed. So it's not a random guessing, like evolution has to just randomly pretty much guess things. In our thought process, we don't guess. We have a huge amount of knowledge. We know how to adapt. That's our long-term memory tells us how to adapt in each particular situation. But the point is that we have to adapt all the time. So that's this process here in the middle. And by the way, this process in the middle, this fast adaptation process, is the reason why we are conscious. And if you ask me a question, so when do I know this process happens to me? And my answer is, that's the only thing you know. Everything that you experience is this adaptation process. You cannot experience the learning process on the very bottom. You cannot experience the fast reflexes on the top. But what we experience as conscious process is this medium adaptation process. There is a recent paper that explains these things in much more detail that you can see. And the paper is so recent that it actually, if you look here above, you see it came from the future. So that's how I know these things. I have contact to the future. Now, the theory is called practopoiesis. This is derived from Greek. Practo means praxis, actions, and poiesis means creation. So basically, the fundamental idea behind is that it's not the computation that we have to pay attention to, but what we have to pay attention to is the process of creating new capabilities for acting, for interacting with the environment. So this is this adaptive process here that you see with the arrow is the process of poiesis, of creation, right? And this is attributed to the famous theory of autopoiesis, which started with such ideas, right? Okay, now, how does it apply to AI? What does it mean to apply this theory to AI? If the theory tells us, okay, AI has to have, if we want to have intelligent AI, we have to have 3 levels of organization. then there are two basic questions. First, what does it buy to you? Why is it better than just 2 or than just 1? And we will answer that question. And then the next question, even more difficult to answer, is how do you create one? How do you provide this system with the proper structure, knowledge, and so on, right? And that question we will also discuss right now. So, first, the question of how do we get, why is the advantage of this process? What is the advantage of this process? And to understand that, let us first consider what is the advantage of having T2 versus T1? What would be required if you wanted to make intelligent system that is only T1, that it has everything here in this gray box on the left? So it doesn't need to learn anything. It knows everything that is there to be known ever needed. So maybe the first initial designers of artificial intelligence may have naively believed that everything could be already pre-programmed in a computer. That you could just say, programmers, program them, put the rules in, and you just work hard enough. Finally, you will make a huge program of a computer that knows everything, doesn't need to learn anything else. Well, it turned out very quickly that it was not possible. Now, think about how big memory this computer would need to have. How big memory would a biological system need to have in order to be born on the planet Earth and already know everything there is needed to be known? This would mean all possible worlds, all possible histories, all possible cultures, all possible languages, all combined. So how big a brain you would need? Well, roughly this size, right? Here's a galaxy. So it's like the size of a galaxy probably, or the entire universe, to know all that right there without needing to learn anything new. Now, this guy looks very confused, and of course he is, because he knows everything about how to live on any of these planets in this galaxy, but he just can't get there. He's too big for it. So the question is, okay, this is T1 system. The question is then, can a T2 system, which has one more level of adaptation, reduce this need for such a huge brain to smaller brain, to get less than 2 kilograms of biological mass? Do you have enough there? Can you do that? And I did actually some calculations. You could approximately calculate these things. So if you take the total number of neurons in the brain, number of synapses in the brain, number of bits that each synapse can store in the brain, you can estimate how much of knowledge can brain store. And then you can assume that everything's maximally optimized, there is no noise, and so on. You can calculate how many different things a brain of that size could possibly do if it is a T2 brain. And it turns out that it's about 10 to the 15 of states. So it's 1 with 15 zeros. Looks like a big number. But is it big enough? That's a question. Is it big enough, or we need something bigger? Then you have to calculate another number, and then the other number is how many states do we need? Or the number is how many states can actually human brain and mind produce, recognize? So that's the question of how many, for example, different visual scenes I can understand. How many different sentences I could possibly understand. Because this number gives me the total variety of the things that my brain can do. And the question is it about 10 to the 15, or is it bigger? Now, this number is difficult to estimate, but let me give you an example how that it could be big. Imagine I tell you a red banana is riding on a pink horse. Most people can understand it, can make an image of red banana, pink horse riding, and so on. But how many different combinations of such weird things are meaningfully understandable to a human person? Imagine now that you can, not only that, you could take the same scene and draw it in many different ways, paint it in many different ways, and that our visual system can understand. And our cognitive system can also understand that this is a red banana riding on a pink horse. And today's artificial intelligence systems are completely lost, right, at that. Now, what is the number of combinations? It's difficult to estimate this number, but I found a way by using the known capacity of working memory. And this number that I get is about 10 to the 20. So this is 5 orders of the magnitude bigger. This is 5 zeros difference, right? This is 100,000 times the brain we have. And these are very optimistic and pessimistic estimates. So I made sure that I'm not subjective, right? So this is probably, what we need is probably much bigger than 10 to the 20. And what the brain can really create, if it was T2 agent, is less than 10 to the 15, right? Because there must be some redundancies, noises, and so on. So we have a problem there. So how do we solve this problem? Well, let me just point out that if we have a T2 system, then we can have a smaller brain than the whole galaxy, but still a big brain. It still doesn't fit in our heads. This one in this illustration has the size of a planet, if it is T2. So if we get from the size of a galaxy to the size of a planet with one step of adaptation, then the next step of adaptation in the T3 system can bring us to the brain of our size. And if we can do that, then we can build, in principle, robots that are as intelligent as us, and in the same time, as big as us. They require as many resources as our brains require, right? Okay. Now, the next question is, how do we build it, right? So what I have shown you so far, you may agree or not, but you may believe me for a moment, that we need a type of T3 organization. And we need something that has these 3 levels of organization. Only this can be possibly flexible enough, intelligent enough to create this variety of behavior that we need. This means that today's AI algorithms that tries to stack everything in this much smaller adaptive structure cannot possibly work. So if Google would like to produce with deep learning networks, what they use today, something that's human-like intelligent, they would have to increase the size of the resources, increase and increase and increase to the size of this huge robot that you have seen, right? It's not going to work, right? So you have to have more flexibility. Okay, more flexibility is not hard to build technologically. It's relatively easy to implement it, right? You just need different types of software, sensory inputs, and so on. But what is really hard to get is that our brain, our mind works on the basis of genes. We have genes tells us what to do, and this is not just one learning mechanism. This is hundreds, if not thousands of principles of how to build our brain from the moment we are born, right? And this has been accumulated through a long process of evolution. It took billions of years, and that's where the knowledge is. Now the question is, how do we get it into AI? If we can get genes, something that corresponds to genes, which would then, we could call machine genome. If we could get machine genome right, then it would be very easy. You just take a robot, start it as a little baby, nourish it, grow it, and a few years later, it's an adult robot, knows everything like a human. But the problem is how to get the genome and not spend 1 billion years in evolution, but spend a few years. That's what AI kindergarten is about. It's about cracking this problem. Now, one of the tricks that AI kindergarten uses is the fact that evolution has already done that job once. And the result of this job is already in our genes stored. So we have to find a way to transfer the knowledge from our genes into the machine genome. If we could crack that, then we don't have to repeat the evolution. We just have to somehow figure out how to get knowledge from our genes to our genome. And you cannot just copy-paste it with a memory stick. No, even if we know the genome, but we don't understand it, we cannot just copy-paste it. We have to do something completely different. Right? And this completely different thing on how to cut out the development time of some knowledge, we have already used this technology quite a bit. We already know this type of technology, and it's called education, right? So what our culture knows, what our civilization knows, is accumulated knowledge over at least several thousands of years, if not longer. And yet, we are capable of transferring this knowledge to our kids. Within 20, 30 years, they pick up a good chunk of it and they can operate. They don't have to repeat the thousands of years of the development of human civilization. There is a method of doing it quicker, of using this knowledge and doing it quicker. And again, in the education, we don't copy paste like with the memory stack the knowledge. We have to do some work, but the work is not thousands of years, it's only a few years. Now what we need to do with AI engineering is a similar process, but not at the level of long-term memory, but at the level of genes. The same trick, but at the level of genes. We have to transfer the knowledge from our genes into the machine genome. Now, do we have any experience in doing it? Actually, we do. And it's called selective breeding of animals. We basically, through selective breeding of animals, we turned wild wolves into nice, docile dogs, right? So we have been doing it, and we're doing, of course, genetic engineering nowadays even more and more. But the point is that it's doable also in a short period of time, a relatively short period of time. How long would it have taken wolves to turn into dogs if we did not interfere? Probably forever, if never. But with our interference, relatively quickly, we could turn them into it. And not only dogs, also a bunch of other animals we could turn into our needs. So if we find a way to combine the fast learning that we see in education with genome manipulation, we can create machine genomes such that the machines do exactly what we need them as robots. The important thing is that for that, to do that, it's not enough to have a T3 agent simulated on a computer, which is a relatively easy task. But what we need is actually T4. And why do we need T4? Because, as I told you, we, the individuals, biological individuals, we are organized at these 3 levels of organization. We have T3 structure. However, how did we come around here? Is through evolution. An evolution process is also a process of changing ourselves, from changing our genes. It takes also feedback from the environment, and it's actually this 4th level of organization. So the species, although individual is T3, the species as a whole is T4. Actually, the entire biosphere on planet Earth is a T4 organization. And we need, if we want to make artificial intelligence that is like us, we need exactly the same structure. We need a T4 structure. So our AI kindergarten is going to have, at the end, a T4 structure. But before I tell you how it will do it, I will give you a little bit of a theory of what it takes to develop artificial intelligence. So here's a little bit more formal definition of a few things. You remember the structure I told you where we have a T2. This is a classical AI that you have perhaps on your phone, trying to recognize your voices, your commands, sometimes successful, sometimes not. Now, what is the key of how does a human engineer create this and understand that? There are 3 different types of aspects of this structure. So I said at the bottom we have these learning rules. And these learning rules, human engineer understands very well. We create them, we understand how they work, we understand how they apply. And that kind of knowledge we can call clear knowledge because it's understandable to human engineer. But then, when you apply these learning rules, these artificial systems, they learn things and fill up some memory with data. These are matrices of huge amounts of numbers. They could represent some probabilities. They could represent synaptic weights and so on. But the point is that this is no more understandable to human. The human engineer cannot look at it and understand what's going on. We just have to use it as such. This we refer to as dark knowledge. It's dark for the perspective of the engineer, of the creator. But then there's the good news. At the end, at the level of behavior of the system, we still can understand it. So although we don't understand this middle part, what the system has learned and how it performs its functions, once we run it and apply it, once it performs its function, we can understand it at the level of intuition. We can tell, well, that's good, that's bad, that's interesting, that's what I want, that's what I don't want. And that level we can call opaque knowledge. Now, this is for a T2 system. If we have a T3 system with additional fourth structure, then we have to have the same structure. At the end, at the top, the behavior of a robot is something that we have to, we can judge whether it's behavior we like or not. Is this what we want or not? Is this what I would do in this situation or not? In the middle, we have lots of dark knowledge that we cannot understand. And then at the very bottom, we have to have understandable things. The bottom requires understanding, because otherwise we cannot even begin to build it, right? So at the very bottom, we have this simple learning rules. And the theory of evolution is pretty simple. We understand it, so in principle, we can do it. Now, you remember T1, the idea of developing first maybe artificial intelligence with T1, that humans understand everything and program everything. This would be this structure, where you would have clear knowledge and producing intuitive knowledge. Well, that we have today in the form of software. Most of our software is developed like this. It's actually developed by human programmers who understood what they were doing and why they were doing. And we, as a user, understand it at the opaque level, at the top, at the level of behavior. It makes sense to us or not, we like it or not, it's useful or not, and so on. Now, when you want to build a T2 system, really, you need this additional level here that's understandable. Then you can build a dark knowledge, something that is not understandable. Now, the requirement is at the bottom that you have something programmable, understandable. And then the second requirement, very important for developing artificial intelligence, is to have learning samples. Right? So you have to have proper learning samples. So what we do normally, traditionally in AI, if you want to, for example, teach a system to recognize handwriting, you give it examples of correct handwriting. So you give, here's some numbers, and you give it what these numbers mean, and then the system runs to it. The interesting thing about these is that they have a T0 structure. It means they don't interact with the world at all. They're just sitting there passively, waiting to be used. Now, look at this. To create T1 agent that is intelligent, we need T2 structure with T0 samples. Now, what happens with T3 structure? If we want to create T3 structure, T3 agent, we need T4 system. So what do we, with the same kind of rules at the bottom, but what do we need as rules, as a learning examples? And as learning examples, what we need is T2 structure. We need actual behavior. It's not enough to give it just pictures. We need actual feedback on the behavior. We have to tell it, that's good, that's bad behavior. No, don't do this. This was nice, good boy. That's exactly what happens in the real kindergarten, right? You have to interact with kids. You have to tell them that was good, that was bad. Give them examples. Do something yourself as a teacher so they would see and so on. So you have to build T3 agent. You need T4 system with T2 examples. So we can generalize that. And here's the law of AI creation. This applies to creating any form of AI, any level of complexity. To create an Tn agent, we need Tn plus 1 creation system and a set of Tm samples where m is less than n. If you follow this rule, you can create any AI you want. Now, we follow this rule and create AI kindergarten. And this would, to create it, we would have 3 components. The first component is the simplest one. It's direct engineering. Direct engineering means just whatever we can find a shortcut, whatever we happen to understand, let's not waste time, just build it directly. And there's many things we can directly understand. We figure it out how it works. Scientists figure it out somewhere. We just build it directly without worrying. But it's also, this only can get us that far. We have to go into the dark knowledge. And for that, we need Playroom and Incubator. So let's see what the Playroom is. Playroom is basically a process of transferring knowledge from human to machine by similar principles by which we transfer knowledge from adult human to child, or 2 persons interacting. The important part of this is that you transfer knowledge from lower level of organization. You don't take it from the top. You take it from a deeper level, from your long-term memory. And how does it work? You have one agent here, you see on the left, that interacts with the environment, has its own structure. The green part is the environment. Then you have another agent that also has its own structure. But the point is, the necessary condition is that they share the environment. There's also a few other conditions. They need to share the goals and so on, but I'm not going to go in details now. They have to share the environment. If they share the environment, if they work on the same problems, they start interacting with each other, they become environment for each other. And as they become environment for each other, there's a very nature of these adaptive systems is such that they tend to become models of each other. They tend to become similar to each other. That's just a very, I don't have time now to go into details, explain why, but there's just a tendency of the system. So they tend to share the knowledge. The more they interact, the more they tend to share the knowledge. So how do you make sure that the knowledge goes just in one direction? You simply freeze the learning mechanisms on one side. And then you have knowledge transfer, basically. You have to make sure that one side doesn't learn. There's different ways how you can do it. In a technological system, it's very easy. You just shut off some part of a software, for example, so it doesn't really learn anymore. In a human, it's a little bit more tricky, but it's doable as well, and that's what we do all the time. How do you make sure when you're a teacher in a school that kids learn from you, but you don't become them. You don't become childish. How do you make sure about that? It's possible, right? You just have to worry about it, right? You have to have enough knowledge, and then you can do it. So basically what we need to do to transfer this knowledge to machines, we have to transfer different bits and pieces of knowledge of proper behavior. This means that the robots have to behave, you try some things, and they have to get feedback of what is wrong, what is good. They have to maybe observe our behavior and also try to learn from these examples and so on. So this ends up basically that we will have, as this technology develops from simple to more complex, at the end we will have something very similar to real kindergarten where human trainers and educators are playing and training robots. And this is one artistic illustration of what such a playroom may look like in the future. And this job that this lady here is taking is maybe going to be the job of future of training robots, like a teacher. It's like what the programmers do today. This is what people will need to do to develop AI. Now, let's talk about the third part, and that's the incubator. In the playroom, we get only bits of knowledge, and it's not yet transferred to the level of genes. But you get many bits of knowledge. We will have to probably collect thousands, if not millions, of such snippets and bits of knowledge in order to cover properly our own knowledge, the knowledge that's stored in our own genes. And then you have to have process to integrate all these bits into one big agent that knows it all, that takes all this knowledge. And the way we do it will be, again, through the same principle, which is called knowledge transfer theory, not a surprise, where you will now not have any more human-robot interaction, but you will have robot-robot interaction. But in such a way that one robot is frozen has lower levels of organization frozen, so it doesn't change anymore. Then the other robot doesn't have it frozen, is flexible, and can even change its own machine genome. And then they have to share the environment, interact, have the same similar goals, work together on some things. And it's kind of, this whole thing is computer simulated, for example. Could be also made like real robots interacting, but probably in most cases it's the simplest way to simulate everything on a computer. And this knowledge can be transferred from small snippets of robots on the left that came from the playroom into bigger and bigger and bigger robot that has more and more knowledge here on the right. And we just accumulate that knowledge through this process. Now, the way how to integrate the snippets, there could be several ways. That could be some more optimal ways. You don't necessarily want to do everything immediately stuck on one big AI, one big robot, but you want to maybe make small subsets and then bigger ones and so on. And here is one such strategy of how to build it, which is a part of a patent that I have recently submitted. But I'm not going to bother you with details about that. But what is important to understand that this process in Incubator of integrating knowledge is something very similar, very equivalent to process of dreaming. Right? When we sleep and dream, that's what we do. We also integrate knowledge that we have accumulated through the day. Now, this dreaming is going to be a little different because when we dream at the level of our memories, our long-term memories. But what the machines will have to dream up here, they will have to dream at the level of genome. What does it mean to dream at the level of genome? It means you live like a whole life. You don't live just you don't dream a few events like our normal dreams, like few things happen, like half an hour, 1 hour story. You can have a whole life dreamed about. And they all interact. They all come to each other's dreams. They all live together in these dreams. So does it remind you of something? It's very similar to what you have seen in the movie Matrix. It's just the other way around. What in the movie have the machines done to us, what we will have to do to develop AI is the same thing, just the opposite. We have to do that to the machines. We have to kind of have them in the playroom interacting with real humans, and then go into this incubator, the dreaming machine, where they will have to integrate this knowledge among themselves. And they will not know what the reality is, maybe necessarily. But it's all for their good. Now, important is to understand that this process is going to make develop things much faster. So we can roughly say that each of these three components that we have is, let's say, 1,000-time accelerator. Remember, what we need to accelerate is billions of years of evolution into just years. We want to turn billions into ones. So direct engineering is a 1,000-time roughly accelerator because some things you don't have to really evolve. You just figure them out. You do them directly. A playroom is another roughly 1,000-time accelerator because we don't have to repeat the experiments that evolution has done. The results of these experiments are already stored in our genes, so we have to just pick them up. We have our own intuition of what is the right thing to do. We just have to tell robots that this is our intuition, and that this is the right thing to do. That way we save a lot of time. We don't have to repeat all these experiments. And then the incubator also does something very important that additionally accelerates. Really, this process makes really faster, but I will explain to you in a moment. I just want to make one another point, interesting point. And this is the following. The playroom, the relationship between playroom and incubator is very similar to the relationship that we have in our own minds and our brains between hippocampus and the sleep, and the process of sleep and dreaming are on. So what we know so far from neuroscience is that hippocampus is very important for fast acquisition of explicit memories. And throughout the day, our hippocampus is very busy acquiring this information. But after that, this information needs to be integrated with the rest of the brain, mostly with the cortex. And how do we do it? But during the rest, during the sleep, during dreaming, we basically replay what we have seen and lived through the day. And that way, the whole thing gets transferred to the other parts of the brain. The knowledge gets transferred to the other part of the brain. Now, Playroom and Incubator do a very similar thing. The Playroom collects quickly the snippets of small pieces of knowledge. What is a good thing to do now? What is a bad thing? And so on. You collect lots of those. And then you have to interact with those and integrate them. There's also a big difference. Our brain works at the level of long-term memories, and the Playroom and Incubator have to go one level lower and work at the level of genome at the end, right? Now, another acceleration process. How we are going to really accelerate this thing? That evolution has also done one more thing for us, ready to use, so we don't have to experiment and waste time. And this is the actual sequence of evolution, the actual sequence of events that happen during phylogeny of the species, so it means during the evolutionary process, but also during ontogeny, during the development of an individual. Right? So the evolution has figured out what is a good thing to do first, what kind of behavior, then what fits well on top of it next, then what fits well on top of it next, and so on. So what's the sequence? We can find out in the biological literature, in comparative psychology, in comparative neuroscience, and so on. And we have to follow this sequence. And if we go to follow the sequence, then we can do the following trick. It happens so that the development of the species and the development of an individual, they're parallel processes. They're quite, not identical, but they're quite similar. So whatever happened late in the development of a species, it also happens late in the development of an individual. And if we use that, we can use the following trick. We can train our AI first with simple things like taxes, like simple rules, avoid damage, and so on, and then go to more complicated, like navigating space, using language, and so on. But at each stage, we don't have to take a new version of a genome, start from the beginning, make a little baby with this genome and have it live a whole life and make a test whether it will survive and procreate. That's what evolution did. And that's really expensive. It takes so much time. And every change you make, you have to repeat the whole life. Repeat the whole life. There's lots of computation, lots of simulation. So how we can crack it? Due to this parallelism of these two processes, the evolution and the development, we can actually do something that evolution couldn't. We could mutate the gene of adults. So we could have already adult, quotation adult, we could have AI developed to a certain level, and then mutate the genes now. We don't have to go back to the beginning. We can go just from that point and continue and test and develop and get feedback and then develop on the next. So that's what you see here. You see here the first steps on the left. Then the next thing what you see is that adding more machine genome such that we lock the old genome. We keep it, but we lock it. We don't change it at first, and then we test it against the environment. Locking the old genome also has the effect of locking the long-term memory, or here I call it IdeaTech. I didn't mention that, because that's the place where we store our semantic knowledge. This reminds us that this long-term memory doesn't work directly to produce our behavior, that it's still there's still very abstract, conceptual knowledge that we need to apply once again in the real-life situation to produce this working knowledge, and then we can interact with the environment. Right? So it gets frozen effectively as well, once we have frozen the machine genome. But then when we have done that, we can do to the next step and so on. Right? But a very good thing to do in meanwhile is to unlock it for a while and have it actually work with its full capacity And this is very good because it's a good test, but also it's very well balances the whole system, makes the whole system function very well good. And how can we do it? Why is it a great idea? Because it's very good, makes a good model of developing AI within certain society. Because you have to have a step where you create a new machine, but then you have to have a step where you basically apply this machine. You sell it out, you sell it as a product, you market it maybe, and then people use it somewhere. And while using it, they are improving the memory of the system. And now you take this improved memory, but after the use, go take that one and then change the genome of that one. This will make the process much more robust and much faster as well. Right? So it's a good also a business model, if you like, to develop great technology at early stages and continually improve it. And at the end, we should be able to create a robot that's intelligent, kind of like us. Now, one question is, how long would it take? Does it take 100 years? Would it take a couple of years? I don't really know, of course, but we can have some hints. It takes, to produce a human with such a diploma in a hand, how long does it take? 20 years at least, right? If it's a really hardworking, smart kid. And we can take this number as an indicator, that as a reference point, right? It takes a human, to create a human, 20 years. Now, if we, and we have all the shortcuts and all that. Now, if we presume that we have all the resources we need to work on it, and we presume that this becomes a popular thing, as popular and as attractive as, for example, a PC computer was, or internet was, or a cellular phone was, where everyone wants to use it, everyone wants to be part of it, everyone wants to help. Then comes a lot of resources, also investment, financial, and so on. In that case, we may think, okay, in that case, we can begin thinking from that point on, when we have lots of resources, how long it takes. 20 years is a reference point. Then we see how we are as things go on. Probably, we cannot expect much quicker than 20 years. But also, if we have all these resources, I don't see any reason why it would take much longer. Maybe 30 years, 40 years. I don't see a reason why it would take 100 or 200 years. Right? But again, I don't know. So we have to try to know. Now, the last thing I want to talk about is safety. Right? So it's very important that this is safe. And there has been lots of talk lately about AI being potentially really dangerous, AI taking over the world, turning us into paperclips. You know that story. The idea is that you would develop a really super intelligent machine, but give it a really task to create paperclips, as many paperclips as possible. And the machine is super intelligent and has the end goal to create paperclips. And what it does with its super intelligence turns everything into paperclips. At the end, it even kills humanity because they are not paperclips. It needs more paperclips, so it turns us into paperclips. How do we make sure such things and mistakes don't happen? And to understand that, I will walk you through a little bit through the history of other inventions that we made in our past, and how all these inventions basically emulate human capabilities, and how we get also superhuman capabilities. What does it really mean? And these all may have started, let's say, for example, with the invention of hand axe. A hand axe is very good for ripping animal skin, much better than human bare hands, than your fingernails. So you get superhuman capabilities already there immediately, as soon as you have the invention. But the important thing is that this is domain specific. Now the next invention, bow and arrow. Really good for throwing spears. Immediately superhuman capabilities, but for the limited domain, only domain specific. And the same with the writing system, right? Memorize words. Superhuman capability, immediately you can have it for hundreds, thousands of years written down precisely, accurately, and so on, but domain specific. Pretty much everything we invent, as time goes on, is domain specific. It has a superhuman capability, but it is domain specific. And also these boxes get smaller and smaller because they have, over time, less and less impact on the ability of our species to survive. So the first things have much more impact than the later things. They're a lot less important. But occasionally there are little bigger ones that happen. Like, for example, this one here. This could be Industrial Revolution, really great thing that happened. And then from that follow lots of things afterwards. Then another one maybe is invention of a personal computer, internet came, and so on and so on. Important things, all these things are domain specific. A handheld calculator is superhuman capabilities in ability to multiply numbers, but that's it. That's where it is limited. Personal computer, superhuman in the search database, but that's it. Now, building such AI through AI kindergarten may be another important step. Big important thing. It could help us solve engineering problems, all kinds of things. But it will necessarily be domain specific. We cannot possibly create intelligence that's beyond what we have. And this is the law of AI creation that I told you is preventing us from that. To create such intelligence, we have to have all this, we have to give it all these samples. Otherwise, we cannot create it. And we can give only the samples of the intelligence that we have. We cannot give it anything else than what we have. Now, if you imagine here that there's a third dimension of some sort of intelligence that's not humans, from some other planet or whatever, we cannot give it to them. We cannot build them because we have no capability to give them samples of that. So the law of AI creation tells us that there's no way that we can build intelligence beyond. Well, of course, we could do through raw evolution, but this would take billions of years. That's a completely different story. But through AI kindergarten, we cannot do it. We can only transfer our own knowledge. And what will happen most likely is that we will just give it a part of our knowledge. We will never give it everything because we will not need it. We cannot give them the knowledge. It's really hard to give them the knowledge of what is it like to be hungry and then have a good meal afterwards. They will never understand that properly because we will never build them really physiology of being hungry and all that. There will be no market need for it. So they will always be a little bit lost if you if you have a robot at home do things for you, it's really good and well, and then some new situation happens that they never knew before, and it's this kind of situation where it's something human that robots don't have. They will have a hard time figuring out what's going on because they never experience it, right? Like we humans also do not understand each other if we didn't live the same type of life, right? If we don't know really what, how is it to be an astronaut because we haven't been there, right? So astronauts can talk about themselves stuff that we cannot understand. Same thing with AI. If they don't have the hunger, if they don't have the sexual drive, if they don't fall in love really physiologically, the whole thing, they're never gonna get it completely. So they're always gonna be autistic a little bit. And that's really good news because there's gonna be still lots of job for us. So lots of things. We will at the end make decisions. We'll all be CEOs of our kitchen at least. But they will do these rough things, hard things that are kind of boring for us. We figure it out, and it's not any more interesting, it's not any more challenging. That's what AI kindergarten can produce. It cannot possibly produce intelligence that is way out there and that it kind of figures out how to rule the world. They will always be obedient. There's one more thing that's important that we have to worry about, is that we could possibly train it to be mean and evil and give it this type of feedback. This is like someone selectively breeding wolves, not to produce dogs, but to produce even meaner wolves, more aggressive, bigger. No one has ever done it. So if you look in the history of mankind, we don't tend to do such stupid things. Maybe someone has tried actually to breed wolves like that and make them meaner and more dangerous, but we never heard of him. And guess why? Right? So we are probably not going to be so stupid to train AI to be selfish, to be mean. There is this dark part of human, we have to admit. We go and create wars. We go and try to rule the world. But that's a result of our own evolution and our own circumstances in which we evolved. We had to do it to survive. The previous guys who didn't have these drives didn't survive. We actually just won over them. Now, we are in a charge in our kindergarten of the evolution, of what things will happen. We will choose, like we have chosen in the past for all other technology and everything else. Our natural instinct is to choose the thing that's good for us, right? So even when you educate your kids, sometimes, when they get to be teenagers and start to rebelling, you want to change their genes, right? And with robots, we can do that, and we can make them actually happily obedient, right? So if we can turn, without having a theory, much of a theory, we can turn a wolf into this little cute thing. We can also make sure that our AI is safe, right? So let me make conclusions. To create strong AI, or biological-like AI, or close to human-level intelligence AI, we need three traverses, not two as we have today. But for that, we need to create it, we need 4 traverses. To create 3 traversal agents, we need 4 traverses. And to create it quickly, we need AI kindergarten. So to cut billions of years of evolution into small numbers of years, and it's safe. Thank you very much.